Well, where we left things on, so we look at this check complex. Oh, sorry, check complex, and we look also at the Beatrice-Reeves complex, and now we're going to look at the alpha complexes. Alpha complex. For that, for the alpha complex, we need to look first at the Voronoi diagram. The Voronoi diagram. So the Bernoulli diagram is something that they use in combinatorics. Well, you can just start with a set of points in a large dimensional space. To have an example here on the board, I'm going to use just 5 points. 5 points. And we consider the sets. So I have 4 points, and I consider the sets B sub A, which are the elements on Rm, such that the norm between X and A is less or equal than the norm of X to B, with for all B and S. So this means that the distance between all the points in this region are closer to A than the other points. Right? So, for example, in this case, we just need to take the points that are at the same distance between these 2 points are the ones that are in the perpendicular bisector of this segment. How is this line called in English? Perpendicular bisector, just like that? Or is it, well, in Spanish it's mediatriz, but in English? Okay, so nobody knows. Nobody knows. Okay, so then you take the perpendicular bisector, which, so that means that the points in this line are closer to A than this point, right? Sure. Are at the same distance to this point. So points that are in this side of the line are closer to A than this other point. Mm-hmm. So if the same happen with this line, the points on this side of the line are closer to A than this point, right? And you can do the same with all the other points. For example, this is if you take this line and you take the perpendicular bisector, and you take this line and the perpendicular bisector, you get a region. This region is what we call B sub A, right? So this region is the points that are closer to A than the rest of the points. And then you have that region, and you get all the regions for each of the points. We need the other perpendicular bisectors. For example, this one fortunately passed to this point, the perpendicular bisector, and so you got this line that goes in that direction. And then if you take the perpendicular bisector between these 2 points, it's going to pass through here. And if you take the perpendicular bisector, this point is going to pass through here. It's going to be perpendicular. And there is another one here. It's going to pass through here. So that gives us 5 regions, each one per point. So and this is the edges of that region, of those regions, yeah, like this. This is called the Voronoi diagram of these 5 points. But I'm gonna paint them in purple so you can recognize them from the rest of the picture. So you have these 5 points in purple, and that give us 4, in this case 5 regions, each one per point. Right. This is the Voronoi diagram, and we are going to label all the regions according to the vertex, to the point. Okay. So B sub A is going to be B sub B. B sub A. Okay. So far, so good, right? Okay. So from this diagram, we can construct something that is called the, I don't know how to pronounce this, is I think the Delaunay complex. Delaunay complex, right? Then the Delaunay complex, which is constructed just in it just is the subsets of S. That S is just the set of purple vertices, such that the intersection of this Voronoi cells, these are called Voronoi cells. Voronoi cell. This is Voronoi cells is not empty. This is just a way of constructing a complex associated with these 5 points. Well, this is the Delaunay complex. So you can work with this complex and try to understand this structure of these points. But there is another complex that is very interesting, which has an cell, or all the cells have boundary. Yeah. So the intersection between cells is just in the boundary, as a matter of fact. Yeah. So then we define the alpha complex. The alpha complex is by taking defining, you define RUR, which is the balls. Well, you define RAR with given A in S. You define an R, a real number bigger than 0. You define R sub A R to the intersection between the ball or radius R in center A with the corresponding Voronoi cell. So that means that I'm going to take balls of certain radius. So the intersections, if the ball is inside, it's just going to be the ball. But if it is bigger, it has a bigger size. If there are points in the ball outside of the region, I'm just going to take the intersection. So some of these are some of these arcs are going to be something like this. For example, here you're going to take a circle around this thing. So this is going to be so we are going to take just this part. This is R sub A R. That's it. And in the alpha complex, the Delaunay will be the nerve of the Voronoi cells. Yeah. This is like an intersection of radius with balls of radius R. Yeah. Yes, just a parameter. Yeah. Radius. Yeah. The radius. So then the alpha. And so the alpha R is going to be just the the nerve of these R's. Alpha R is going to be the nerve of this covering of these sets. The nerve of this, which is just the sigma set of this, such that the intersection R is not empty. Now, so this is a variation of the check complex. The check complex, you can build a check complex using balls centered on each of the vertex with the radius R. But here you're copying off these balls with the Voronoi cells. In this way you don't have. In this way you are avoiding a lot of. You are reducing the number of intersections of this complex. As a matter of fact, you are what you're doing here is you're reducing the dimension of this complex. Yeah, because you won't have on all these vertices, as you can see, you have just three cells intersecting. So you won't be having four quadruple intersections or 5 points of intersection. You won't have cells. You won't have simplex cells of dimension bigger than 3, bigger than 2. Well, you can have dimension 2, which has 3 intersections, but you cannot have anything bigger than that. And the nice property about alpha. So one of the properties is the alpha R is actually isotopic. It has the same homotopy type. The homotopy type of the the balls of X. So this one doesn't change the homotopy type, but also alpha R can be embedded in the same dimensional space in Rm where the points live. So this means that the alpha R simplex has dimension of most m. That will give us a much smaller simplicial complex associated with the cloud of points. But it comes with a cost on computation, because you have to compute the Voronoi cells and the intersections. But at the end, you will end up with a much smaller simplicial complex representing your data. Now, and you don't lose the part of having a complex representing the same homotopy type of X. So this is a very nice another very nice simplicial complex used to study data sets, point clouds. So that's the end of simplicial complexes in data analysis. So that's the kind of simplicial complexes that the people work with, and probably this is one of the most useful, but not the most used simplicial complex. I think the one that the people use the most is the Vietnamese ribs, because it's the fastest one so far. But this one I like because it's smaller. And it's and then now one of the things that we need to learn is homology. So we're going to learn homology, but the way that we're going to learn homology is a variation of homology that is called simplicial homology. So we're going to learn how to compute a two simplicial complex, but homology has a more broad, can be computed for a more extensive family of spaces, not just simplicial complexes. So, but in the case of simplicial complexes, can be actually computed using the computer. Yeah. Okay, so this is how it's done. So we start with a triangulatable space, and so that means the X is the geometric realization of a simplicial complex. As an example, we can use the annulus. This is the annulus, which is S1 cross I. Right? But as we wanted to be like, we want to look at this annulus as a simplicial complex, we can use a triangulation, and this is the one that we are going to use. It's a triangulation. This is a decomposition into 8 triangles. Okay. So, and we define Cn, well, just Cn. I'm gonna change this later. It's gonna confuse with that one. So this K, the simplicial complex, Cn of K, as the C, the free abelian group generated by the n simplexes, which is of K. So in this case, so for example, here we have 1, 2, 3, 4, 5, 6, 7, and 8 vertices, right? So when we talk about C0 of K, we meant the sum. So we meant we are going to construct the free abelian group generated by V0, V1, V1, V0, V1, V2, V4, V1, V2, V1, V2, V3, V4. Okay, so V1, V2 up to V8. So generated by the 8 vertices, which you can see it like you have C multiplied by V1 plus C multiplied by V2, and so on, C1 multiplied by V8. So the elements of this thing are just formal sum and operation. So it's a formal sum of elements of vertices multiplied by integers. So for example, a typical element looks like it's something like 5. Well, not typical. An element of C0 looks like 5B1 minus 2B2 plus 3B5, right? This is an element of C0 of K. It's just formal sums and products, nothing more. Yeah, this is the first time that we learn about this stuff. We try to give meaning to this, but this doesn't have any meaning at all. Yeah, it's just formal sums operation. So I just taking 5 times vertices 1, 2 times vertices 2, and the subtraction of those 2, which doesn't mean anything. It's just okay. So once that you have that, well, but why do we do this? Is because we want to identify. We want to identify poles and parts of these things that represents cycle. And the way that we're going to identify cycles is algebraically. That's what we want to do, doing algebraically. So this object is just required for formality, but the thing that is going to help us to identify cycles is the boundary operator. So for this, we also want to need C1 of K. C1 of K, which is what? Which is basically the same, but now is just formal sums of it. So I have here C, the vertex B1, B2, which is an edge, plus C, B2, comma, B3, and so on. How many edges? Well, I think we have 4, 4, or 8, plus another 8, 16 edges. So at the end we have 16. It's a 16 summons, 16 additions of C here. Yeah, 16 of them. So the rank of this group is 16. Okay, and that one is 8. So, and well, we define a boundary operator. Boundary operator, which is gonna, what it does is that we're gonna start with the one that is the simplest, which is the operator that goes from C1 of K to C0. Okay. So this operator is good. What it's gonna do is just gonna behave nicely on this structure, but whenever it sees an edge, for example v1, v2, the result is gonna be the boundary of that edge, but with subtractions. It's gonna be v2 minus v1. If I see v2, the boundary of v1, v3 is gonna be v1, v3 minus v1. That's what you're gonna get. So the thing is that this, and when I said it's gonna behave nicely, I mean whenever I have something like 2 times v1, v2, because this is an element of this. This is an element of C1k. This is the boundary. This is the boundary, and this is 2. It's gonna be the boundary. It's gonna be 2 times the boundary of v1, v2. As 2 times minus 3 times the boundary of v1, v3, which is 2 times v2 minus v1 minus 3 times v3 minus v1. And at the end, we got 2 times v2 minus 3 times v3 minus 2 plus 3 plus v1. So one of the important parts is that the boundary of this thing is going to give you an element of this thing, which is just another symbol, which is sum of vertices, right? So one of the things that is interesting is what is the kernel? What is the kernel? What is the kernel of D1? So what is the kernel of D1? What is the meaning of the kernel? So the kernel, so what I need is something that whenever I take the boundary, it becomes 0. So that drawing is, well, I need to draw it back here. Okay. Well, I can just refer to the drawing. So, for example, v1, v2, v3, v4. So if I consider v1, v2 plus v2, v3 plus v3, v4 plus v4, v1. This is an element of C1 of K, right? So I have v1, v2, v2, v3, v3, v4, v4, v1. This is an element of C1 of K. Is part of the, by definition, it belongs there. All the coefficients are 1, and we are just adding all the edges. So it's an element of this group. So I can take the boundary operator of this thing. Is what is going to be the result of this? It's going to be 0. Yeah, because you have b2 minus b1 plus b3 minus b2 plus b3 minus b4 plus b4 minus b1. So everything cancels out. B2 with b2, b3 with b3, b4 with b4, and b1 b1, right? And so the kernel is detecting loops. Loops is what is detecting the kernel of that thing. So it's detecting whether the set of edges that you choose and the direction that you pick those edges, the addition has boundary 0 means that whenever it's starting a point, everything cancels out and returns to the point, to the original point. That's what is giving you in this kernel. So if there were no other things, and let me see a small example. An example smaller than this one. For example, this thing. This is the one that I usually look at my classes. B2, B3, B4, and you have the edges, which is so if you look at the boundary of, in this case, you have no two-dimensional cells, no two-dimensional simplexes, and in this case you have C1, which is of K, C2, C0 of K, and it's a boundary. So and there is nothing here like there is C2 of K is empty. It's 0 because there are no two cells. So that means that this thing is 0. So the boundary one, because you have B2, B3 is being mapped to B3 minus B2, B1. So you can try to understand this map, but one of the easiest way to understand this map is thinking of it like a matrix. Mm-hmm. Basically, what you're receiving here, you have, and this is generated by the edges, right? So you have C B2 B3 plus C B1 B3 and so on. And so so an element here looks like a linear combination of these edges. So would you have to use the coefficients to decide where is what kind of element that you're gonna get here. So what you do is you just create a matrix that takes B2, B3. So you just say you have the entries, the coefficients, the B2, B3 here, and here you write B1, B2, B3, B4, and you just write here 1, 0, 3, and -1, 0, something like that. I don't know. I decided to do this computation right now, but I think this was a bad idea. Because there are too many edges. Let me try to write them all, which is C1. How many edges are? 1, 2, 3, 4, 5 edges. B1, B2, B1, B2. I don't need B1, B3. B1, B3, B2, B3, plus B3, B4. Well, probably it's a bad idea to continue with these computations. The thing is, if you try to understand the kernel of this delta 1, you're going to realize that this kernel is generated by just 2. This is generated by two elements of here, 2 elements in here, is generated by the vectors V2, by the 2 cycles that you can see here, this one and this one. So there are only 2 cycles here in this V2, V3 plus minus B1, B3 plus B1, B2. So this one, and the other one is the other cycle over there, like B1. This is probably this is an exercise to show that this thing is in fact a generator of the kernel. So these two elements that lives here generate the kernel. So that means that the kernel is actually computing the number of calls of this graph. right? That's why we say in this particular case, we said that the homology of this graph, I'm gonna K prime is homeomorphic to C alpha 1 plus C alpha 2, right? It's generated by 2 copies of C. Mm-hmm. Well, it has 2 copies of C, and it is generated by exactly these 2 cycles. So this tells us that the homology is actually capturing cycles in this particular example. So but we want to take into account the disks. What happens if we add a disk here? If there is a disk here, there is no actual hole here now anymore. If there is a disk, that will mean in this case the C2K is going to be replaced by C times this disk. Mm-hmm. And so with this part here, we are going to include another function, another operator, which is the operator two-dimensional, which is going to take E to its boundary. Mm-hmm. So the boundary of E is going to be just B1, B3 plus B3, B4 plus B4, B1. Our boundary operator is going to compute the boundary like that. So the homology, we no longer wants the homology to be just 2 copies of alpha 1, 2 copies of Z, because in this case, we only have 1 hole, not 2 holes anymore. After we cut out this hole, we just only have this hole. This other thing is not a hole. It is covered by a disk, right? So this is contractible. So that's why instead of computing the homology as the kernel, we are going to divide by this thing. This thing is this thing is exactly alpha 1. But this is alpha 1. So this alpha 1 lives in the image of delta 2. So that's why a natural definition of homology is better to define it like H1 of K as the kernel of delta 1 divided by the image of delta 2. That's the way that people define homology. Yeah. Well, this was like a motivational example. In this case, so going back to the definition, once that we have the boundary operator can be defined in general, and this is a very the way that that is usually defined is the boundary operator takes a simplex and computes the alternating sums of the simplexes after removing one of its vertices. So when you remove a vertex from the simplex, what you get is a face of the simplex. And so this sum runs on all the faces of this simplex, but the faces of one dimension lower, right? So if this has dimension n, this face has dimension n minus 1. So that's why these elements are elements here, and this sum is just a sum that lives here. Mm-hmm. So one proposition is that if you take the boundary of n and you follow by the boundary you take the boundary on n plus 1 and you follow by the boundary of n, this is going to be 0. You can do the computations, and this is always the case. Doesn't matter how you, if you compute this thing, you will get 0. You will have a lot of removing double vertices. They are gonna cancel out with this thanks to this sign minus sign here. It's going to appear twice, and then everything is going to cancel out, and you're going to get this identity. This is always true. Doesn't matter the dimension. And thanks to this fact, like you have the Cn plus 1, the boundary Cn, and then the boundary n and Cn minus 1, and this thing is 0, that means that the kernel of En, which are the elements that go to 0, contains the image of Tn plus 1. Mm-hmm. So the definition is the homology of this simplicial complex is the kernel of Dn divided by the image of Dn plus 1. And this is a group called the homology of the simplicial complex. We can try to do the computations for this particular example. I think it's too big. But yeah, that's the homology. So any questions? Okay. So if we compute the homology in this particular case, we're going to notice for example, in this case, we're going to notice that we have more cycles here than the other example. For example, we have this curve here, B1, B2, plus B2, B3, plus B3, B4, B4, B1. This one is a cycle because the boundary of 1 of alpha is 0 again. And also if you take beta, the one that goes from B5, B6, plus B6, B7, plus B7, B8, plus V8, B5. This one also, its boundary is 0. So that means the alpha and beta lives in the kernel of D1, boundary D1. So you have these two cycles, this cycle and this other cycle, living in the kernel of delta 1, right? In the kernel of delta 1. But the difference, what happened in H1 of K? H1 of K, remember, H1 of K is the kernel of delta 1 divided by the image of delta 2. So we know that this alpha and this beta, these two elements of C1 lives in the kernel of the delta 1, right? These two lives here. But my question goes in the direction, are they equivalent on this quotient? So how to know if two elements here are equivalent in this quotient? This is a group, and this is a subgroup, and we are taking the quotient, right? The quotient of groups. So if two groups are equivalent, that means that the difference, so two elements alpha and beta are equivalent if and only if alpha minus beta lives in the image of delta 2. That's the definition of homology. So they're going to be homologous if and only if they live, their difference is in the image of delta 2. That's the meaning of this thing. So are alpha and beta homologous? Yes, they are. Yeah, but to see it, you need to construct a two-dimensional simplex a two-dimensional as an addition of two-dimensional simplexes, that its boundary is exactly alpha minus beta. So in this case, I'm going to take each of these faces, F1, F2, F3, F4, F5, F6, F6, no, this is 4, 5, 6, 7, and 8. I got 8 faces. I mean, these are all triangles, right? So what happened if I take the boundary, the operator, the boundary operator, the second boundary operator of F1, for example? The boundary operator of F1 is going to be B4, B1, which is this H plus B1, B6 plus B6, B4. And what happens if I take the boundary operator of F2? F2 is right here. This is gonna give me B6, B1 plus B1, B7 plus B7, B6. If I add these two, B6, B1 is going to cancel out with B1, B6. By definition, I never say the definition, but by definition, B1, B6 is minus B6, B1. If I permute the vertices, it changes the sign. There's something that I forgot to mention. In general, I will have that this simplex is going to be minus 1 to the sine sigma of V sigma 0, V sigma I, sigma n. Yeah. So for everywhere, sigma is a permutation. So the number of transpositions that I need to do in order to come from this permutation to this one is just change the sign of the simplex. This particular identity is added to this group, right? In order to be able to cancel out these two. So we are going to cancel out these two. So this H here got canceled. It's the other color. So this H here, which is B1, B6, got canceled when I add F1 and F6. If I add F2 and F3, the same is going to happen. This is going to get canceled. If I add F3 and F4, this one is going to get canceled. This one is going to get canceled. This one is going to get canceled. All of the ones in the middle are going to get canceled if I take the boundary. If I take the boundary of F1 plus F2 plus F8, all of the ones in the middle are going to get canceled. And the only ones that are going to survive are this, and this, the ones at the boundary, the red ones, and the blue ones. But if you notice, the red ones are just is just this one, B4 and B1 in the right direction. And it's also the one B1 and B2. And if an F6 is giving me B6, B7, which is right here, B6, B7, but it's not giving me B6, B7 in the right direction. It's giving me B6, B7 and B6, B7 in the opposite direction. Okay. So this is minus B6, B7. And so after I add up all of these things, this is going to be, you can check it, you can make all the computations. This is going to be alpha minus beta. So alpha and beta are equivalent in this quotient. Okay? that means that this curve, this red curve, and this blue curve are equivalent, are homologous. So homology doesn't separate or doesn't distinguish curves that are compound like a surface. So the blue curve and the red curve becomes one curve, just one curve. So it's just this homology is detecting that here is a hole, and it's represented even by the red curve or the blue curve or any other curve that looks once around. So that's how homology works in this case. Well, okay. So homology is, well, this is just the introduction to homology. Homology has a bunch of properties. Well, once that you define it like this, oh my God. Where is the eraser? It's always moving board to board. Oops. So I hope that clarifies or help you to get an intuition of what homology computes. So some properties of homology properties is that the first one is that H does not depends on the homology type. Of X, which is so if I use the same space, if I see a different space but with the same homology type, the computations of the homology are going to be the same. So that's why Pieter Reeves or alpha complexes are important, because they preserve the homotopy type. Otherwise, you are computing something different than the actual union of the open cover. And so, and then another thing is that also, well, probably this one had to be conferred. Well, anyway, so another thing is the Hn of X wedge Y, Hn of X plus Hn of Y. Some other properties like Hn of X is the sum of X alpha, where X alpha are the pad components of X. So your space has different components. The homology is going to be the sum of the homologies of every space. And if A is a subspace of X, of maybe a subcomplex, then you will have the Hn of A. It is Hn of X. This, and then Sn minus 1 of A, and it starts over again. This is what is called a long stack sequence. Well, in algebraic topology, it's really important to write a list of these properties, and all of these properties are helpful for later computations. But basically, because in algebraic topology, you are working with very general and complicated spaces, and you want to state properties about those spaces in general. So you need to write relationships between the space and pieces of the space and stuff like that. Another one is probably it's not necessary for the purpose of this class listing all the properties of my God, just no one can connect now to the network. Okay. So let me check just one particular example that we are going to need is A0 of X. A0 of X is, well, in order to write some examples for later computations, I'm gonna basically be using A0. You notice that I talk about HN, right? So that means that we in fact there is no just one homology that we are computing. We are computing one group of homology for each dimension, right? So we're computing H0, H1, H2, H3. So for a space, we have different homologies of different dimensions. So the one that is pretty easy to compute is H0, and this is very easy to understand because this one is C0 of X. Well, this one, in the definition that I wrote, is not clear what is the exact value of this one because I didn't define the boundary operator 0 because the definition would be kernel of this delta 0 over the image of delta 1. But I did define delta 1 to C0, but I didn't define delta 0. So basically, but this one is actually defined just as the 0 map, the 0 map. So everything is being mapped to 0. So the kernel is actually the whole group. And so this is C0 of K divided by the image of delta 1. 0 of K. 0 of K divided by the image of delta 1. So, but the image of delta 1, remember, is just, well, the intuition here is that if you have an edge, the image of delta 1 is going to be y minus x, right? Y minus x, which means that this implies that x is equivalent to y in this quotient because its difference is the boundary of something. So here, everything is generated by the vertices of K, and every pair of vertices are equivalent if they belong to the same edge. So if I have something that is connected, if I have a path connecting a vertices to another one, that means that x is equivalent to x1, x1 to x2, x2 to x3, x3 to x4, C. So C and X are equivalent. So everything that can be connected to a path are going to be equivalent. So that means, so this idea shows that, well, explains a little bit. I don't want to do all the actual computations that are not really hard, but this is for the case of simplicial complexes. This means that H0 of K is C to the n, where n is the number of connected components. So H0 is the one that determines the number of connected components of your simplicial complex. If you're working with a graph and you don't know if your graph is connected or how many components it has, you can compute H0 of K, and it's going to give you the number of connected components. So it's going to give you the group, which is going to give you you can determine the number of components by looking at the dimension of this space. Well, that's something that we do. And so in order to do example, we're going to be using this thing. If you want to compute the homology of a simplicial complex in general, just what you have to do is linear algebra, basically. So you have if you have a map, there is this theorem. You have Cn plus 1 k, and you have here Dn plus 1, and you have Cn plus n of k, and you have Dn and Cn minus 1 of k. This thing is the dimension of this thing is going to be C to the number to beta to Bn. Bn is the number of simplexes of dimension n. And then we have here the C to the Bn minus 1, and this one is C to the dimension Bn plus 1. So the technique to compute the homology is to present. So the technique is write delta n plus 1 as a matrix. So here you put the n plus 1. So the columns represent the n plus 1 simplexes, and the rows represent the n simplexes. And you write here the boundary operator, like I said before. You just compute the boundary operator of an element, and you will get a sum of element of n simplexes, and you put the coefficients here. You just write all the coefficients. So if this is the element E, and this is n1, well, I'm gonna write F, E1 plus N2 E2 plus N3 E3. You're just gonna write in the N3 E1 E2 E3. You're gonna write N1 into N2 and N3, and zeros on the other entries. So that's kind of the way that you fill up the entire matrix. Once that you have the matrix, you apply an algorithm that is called you compute the CIMAT normal form, normal sum, which is just by applying row operations and column operations, you transform your matrix into the form D1, D2, into the diagonal form with a lot of zeros. And probably some columns of extra zeros. But yeah, you have a diagonal here. But D1 divides that D2, and so on, and divide dk. So this is the Smith normal form, and you can compute that for every matrix using columns and row operations. Well, so making row operations means changing the base of Cn. Doing column operations means changing the base of this other part. So the base of this space of this group. You change the base. That would mean adding columns or subtracting columns. If you change the base here, just adding rows or subtracting rows. And just by adding and subtracting rows of integers, you will get a matrix of integers with all these numbers satisfy this condition. This form is unique, and it's called the Smith normal form. It's kind of complicated. Well, it's not that complicated. There are a bunch of algorithms capable of computing it. And so once that you have that, then you just know that the Hn of k in that case is gonna be C d1 plus C d2 plus C dk plus ZR minus K, where R is the rank of the kernel of the N. So once that you have a simplicial complex, is basically an algorithmically you can compute the homology. That's what I want to say with this result. So you don't need to know much deeper. You don't need to have a much deeper knowledge about the meaning of homology. If you just want to compute it, you just can do straightforward and do all these computations. Take every boundary operator, write it as a matrix, transform, get its normal form, and then you will get the homology of the space like this. Here, one observation is that R has to be larger or equal than K, right? Because the image of N plus 1 is contained on the kernel of the N. So the kernel of the N needs to have a larger dimension than K. So that's the way that you can compute homology, and then there is no time for an exercise of how to compute it with a specific example, but yeah, that's the way that you can do it. So, but using Z coefficients is not very common in applications. This part here is torsion. So you have elements that this is not a vector space. This is just a group, and you have elements with torsion. The elements that to a certain power they die, and that's not really common that can happen in data analysis. But as you can see, there is an expensive cost of computing this matrix. So computing this matrix can be really expensive because you have to run the minimal form to compute the homology, and doing it every time it can be really expensive. So that's why most and in the terms of persistent homology, you will know that this kind of torsion it is really hard to handle. Yeah. A little bit over time here. What's that? Okay, so thanks for telling me. Thanks for telling me. Yeah, I think I'm sorry. Yeah, I will extend my time with homology. Okay, sorry. Yeah. Well, persistent homology in the next session.